Hello there, welcome back. So now let's talk about a little bit this pressure distribution, how to save it, and some things that you can see in this plot. The first is also that I would like to point out that sometimes might happen that you are running XFOIL and sometimes you start to getting strange results, difficult convergence, and whatever. So remember that always is this init to initialize, but sometimes you run, it's not saving the polar. So the best way to solve those problems when you see that things are going out of control is just close XFOIL, open a new session, okay? That might happen. You have seen that XFOIL is really fast and the commands are very intuitive, so you can reproduce everything with no problem. But it might happen, I know, especially for beginners, it can happen a lot, okay? Because you're putting too many things here and the solution gets crazy, okay? So I recommend you just to close it. I will do it, okay? So I read in a new plot, a new airfoil, so that this is a new airfoil, the polar, and we're going to talk about that. So I will close that one and I will open a new one, okay? So be advised, no? Have in mind that. So I'm going to load a new airfoil, and here in the my airfoil, you have a short database, but remember also you can go to this website, the database here, you can download many airfoils there. But here we have a few airfoils, and I will choose to read this one, this 6.5.2.10, okay? So I will, the location, airfoils, 6.5.2.10 .dat, okay? Open and see that it's okay. This is the airfoil. I want to point out something about this airfoil, okay? So this is a series 6 that we have seen in theory that have this drag bucket and this other property. But something that you have to be careful in XFOIL is that having scene airfoil. This is a scene airfoil, okay? And it's difficult with scene airfoil. It's sometimes difficult to get convergence. So be advised about that. So see that we don't have many panels, so it might be a good idea to increase the number of panels. So you go in ppower and let me put 200. Enter, and you have here. Okay, so see here that we enter here, we get some basic information here. Maximum thickness, okay, it's about 0.1. Okay, so this can be considered raised in airfoil. That might be problematic, but it still can work. But stuff about 0.06 it can be problematic. Okay, also when you have a small curvature radius here, but this case I think it works. So let's work with this case. Okay, so now I go into Opera. Okay, so see that we're in B6. Let's test that everything is okay. So I would run one preliminary case and see that we're getting the CP distribution, okay, for in V6 case. So the question might be, how do I save this one because I want to plot it, okay? So we proceed in a similar way as the polars, but here we don't have the option to automatically save CP for each angle. Kind of unique to do it manually, but also you can parameterize this. There is no problem, okay? So for instance, remember that you go here, iteration point, question mark, here, you have this option, you go here, CP somewhere right, and you can write this CP distribution. So for instance, I go CPW is CPWR. See that it's telling you that it's going to save that in this directory with this name. You press enter, and now you go here and you should have it here. Open with Sublime Text and see that you have your distribution, okay? So it's saving everything, one single file, okay? So it's not doing the separation between pressure, suction side, or top bottom, or introduce, extrude, or whatever, but then you can do that manually, okay? So you can find, you know what is the maximum coordinate, and then this one, you can create two separate files. Now, this one will correspond information top, the other bottom, so it's not a problem. So see that it's quite easy, you save it there. So the other thing that now we can do, okay, so if you want to save it for another angle of attack, just change the angle of attack and then save it. Be careful not to override the previous one, so change name. Let me go to viscous mode. And I will go Reynolds 3 million. and we have it there. Okay, so I will run alpha 0. And something that probably you realize and see here, look at that here, you have these small bumps here. Okay, those bumps correspond to the point where you have the transition from laminar to turbulent. Okay, we studied this a little bit in the theory, but you have it there. And that information, you see it here. Okay, so we have free transition, okay, and you have it here. So you have transition about 67% and 66% of the airfoil core. So precisely correspond to that. Okay, so this means that you are maintaining laminar flow up to here, okay, and this will translate in a very good property that is low drag. Okay, you have low drag. Okay, so always look at that when you have the viscous flow. Okay, alpha 4, and you will see that, okay, not converge and running just. Okay, and see that, for instance, in this case, we have the onset free transition immediately. So in the top size, you have it immediately, but in the bottom, see that you have this small bump here. This corresponds that you have laminar flow up to here. So you have here positive pressure gradient and then burst pressure gradient. So when we're talking about the theory, also this is the all this is the pressure recovery, and it's a very smooth pressure recovery. This is very desirable property. And if I go back to 0, see that here also it's kind of a flat pressure distribution, or opposite to the NACA 2412, as you recall. Okay, it's very different. Okay, so these are very desirable properties. Okay, it's low drag, also good lift production, and also we look at the moment as well. So what is interesting here that we can control in XFOIL, we can control it somehow. We can control the transition. So remember that over the potential solution, we're also adding a viscous correction, solving some equations. I'm not going into details, but in the documentation that you have with XFOIL, so as you go here in the source code, remember this file here, you will have a very good explanation about that theory. Well, not so very good, but then you will go to the papers. So you have everything explained there. But basically you are solving now the boundary layer equations with some stability transition criteria, okay, and there are some Sommerfeld equations involved and whatever. So the thing that, what will happen, so see that here we have laminar flow here, then onset of turbulent, and here. So we know that here friction coefficient is low and here is larger. So what will happen if we somehow force the flow to become turbulent, let's say here. Okay, so also we saw in these slides that we can force that, when actually in some physical airplanes it's very desirable to force the flow to become turbulent to avoid these laminar separation bubbles, because they can be very dangerous. So that can be also controlled in XFOIL, and that is what I want to show you. So as we go here, no interrogation point, and see here that you have many options, and we're interested in this one, VPAR. Okay, so these are change boundary layer parameters. So as we enter VPAR, see that is another submenu, and see that here is giving you some options. So the options set by default are this one. So this is transition top side, bottom side. One means is natural transition, but I can say I want transition at 0.2, means 20% of the core, so you can force that. And this is related to, this is the critical amplification number. Okay, so also we can play with this value. Most of the time this is okay, but depending on what you are doing. So lower values means larger intensity, turbulence level. Okay, so if you put 0.2, it means that you have a large intensity level. If you put that one to 14, 16, is a low intensity level. Okay. And these are some parameters also related just to the numerics. I'm not going into detail about that, okay, about formulation and how to solve equations. But we're interested in this, forcing these parameters. So if I go question mark there, see that you can control that here. So we're interested in this one. So see that you can here change critical amplification number is this exponent or EN model that we're using. And you have some other options there. But the important one are these two, and I will play with this one. XTR there. And see that it's talking about these trips lines, no? To trip the flow to become turbulent. So pay attention to the drag coefficient that we have here, okay? So see that in top surface, I want to force the flow to become turbulent at 0.1 and the same in the bottom. So now you set that to control this, you set that, just show, and it's showing you the parameters. And now we're ready to run. So let's run this simulation again, alpha 0. So see that CD00376, if I run this one, as expected, 00799 is larger, okay? So see that now we're forcing the flow, see, and you see the influence here to become turbulent. So these have a lot of implications we saw during the lectures. Now, the most important one is that you are kind of bursting that laminar separation bubble that in some cases can be very dangerous. At high Reynolds number 3 million, they are not very dangerous, but there are sometimes you can operate at lower Reynolds, about 500,000, 300,000, 100,000, and there those laminar separation bubbles can be really dangerous because it will occupy, a large, percentage of the airflow, and they can propagate and then they burst, and you lose lift and increase drag. Okay, so this is you see that it's an artificial mechanism just to trigger turbulence. Okay, eliminate that. You are going to increase drag, but well, you are getting rid of that bubble. So let's go back BPAR XTR. So if you want to go laminar, put 1 and 1. So let me go also here. So I run the case and see that this is the parameters that we have. So let me take a screenshot here just to compare values. Okay, so now I don't recall if I have natural transition, alpha 0, and this is it. Okay, so see that now we have these values. So we compare with the previous one, see that total drag, okay, in the previous one where our trigger is larger, okay? But what is interesting, look at that, okay, all the values are larger, okay? But sometimes it may happen that the pressure drag CDP, the pressure component, is lower, okay, and your total drag can be lower because this is the one that is going to contribute more. So it is a balance, it's a compromise, okay? In this case, it's not this is not the case, but some occasions it happen. I see that also by adding that one also we're losing a little bit lift, okay, moment, but see that by increasing the turbulence, see that we're gaining in the moment something, okay? The moment coefficient, see that is lower than this one. And this is something also that we should always look at, the moment coefficient, okay? Because it's very important for the stability part, okay? Because to compensate this pitch down moment, we need to add a force in the tail, or if you have canards, you will need to add some force there, and now usually that to trim the airplane, that will add drag, but also you might lose some lift, okay? So probably as you start to do now the whole configuration, maybe at the end of the day, this, even if you produce more drag, this will be better because you have lower trim drag, okay? So always look at that component. Okay, it's moment, all coefficients are important. So that is what I wanted to show you. And now also let's play with this critical amplification number, okay? So as I say, is you put a low value means that you have larger turbulence intensity, okay? So the effect will be, so these XTR parameters that we're using is local and saying in what position of my airfoil I want to trigger the transition to turbulence. But as I do it globally using this one, I don't need to specify that, it will be something global, okay? So let's go again, BPAR. And that you change it here, okay? So values larger than 9, more laminar, lower than 9, more turbulent. So I will go here to the lower value, okay? Show, okay, and see that now I have a global effect, and see that I put it lower, and see that my turbulence intensity here is larger. It's also computing that, as you know. So for instance, let me put here 16, you type show and see that it's a very low turbulence intensity level. So that is laminar. Probably you're working with gliders. This is what you're going to do. And lower values, usually in turbo machinery is where you have that one. But also it might happen that is your standard aerodynamics, you have it, so you put it. So it's up to you, okay? So I will work with 2, a large value. So see that you have large intensity value. And let's run again. So if I go alpha, so what we're going to expect here is that now globally, we have a large turbulence intensity. So we're not going to expect this bubble. Okay, let's see what happens. See that kind of disappear. Still you have some behavior, but see that also globally it have an effect. We can compare again now the CD, how we have it. So see that here, CD in comparison when we trip the turbulence here close to the leading edge. Okay, I lost that file, the previous case. But the value since that is lower, but also moments see that still larger. So triggering a transition to turbulence here close to the leading edge, in conclusion, have a positive effect in moment, but that is something that you need to analyze, okay? So see that this is how to control transition. And also I would like to show you something, also we study how to save the CP distribution. Different airfoil will have different distributions, okay? Be careful about that. So also something that I want to show you, that here we have CP distribution in function of the core, but also we have something here that this plot, they call it here the G width CPV. I don't like this plot, but basically you have these arrows. So where you have the arrows going out of the airfoil means negative pressure, and going in the airfoil positive pressure. So here you can see kind of the distribution. Honestly, I don't like it. Some people like it. Sometimes, yeah. So if you misinterpret this, one can give you problems. Okay, so I prefer to stick with this kind of airfoils. Okay, or of plots. Okay, so see the difference. Okay, so out of the airfoil, negative CP towards the airfoil positive CP. So here CP positive, positive, negative, negative, positive. So as you compare CPX, see that you have here negative, the positive region, negative, and then here in the leading edge, the stagnation point. So it's up to you. Additional plots that you have here with this boundary layer corrections, that you can also here see that you have these commands BL, so you can plot boundary layer profiles, stuff like that, and also you can save that information. Okay, so for instance, okay, BLA, see that here it's giving you the information. Well, you have now those profiles, and see that kind of you have some profiles there. It's difficult to see, but you have now the boundary layer now profile. You have it there with these functions. Again, I just invite you just to see what are these functions. Okay. From fluid mechanics, also think moment displacement and all that stuff. And finally, the other plot that I like to have, okay, it is something that we can also plot that probably is easier to see the effect of this transition, or also we can plot the friction coefficient over the surface. So to plot the friction coefficient, okay, there is another option here. Okay, so let me go here. So see that you have many options. Okay, sequence, grid, B-plot, okay. Boundary layer variable plots. Okay, so we go B-plot. See that is another submenu, and you have here the options. Okay, so here you have a few, the description and everything. So see here that you can plot H, the shape parameters, d star and theta, H velocity, skin friction, dissipation coefficient, amplification rate, all this you can plot it. Okay, but I'm interested in CF. CF, and here you go. So see that you have it in function of the core, and see that here you clearly probably see we see the effect now of this transition point and critical amplification number. So see here that you have laminar boundary layer, and then onset of turbulent boundary layer, and then it's turbulent. Okay, so here clearly you see that when you have turbulent boundary layer, you have more skin friction. Okay, but might happen that your pressure drag is lower, so the contribution will be positive. You will need to analyze that. So you have many plots here. Okay, it's up to you to choose which one you want to use. I like to use this one, but okay, you have it there. Also see that if what we recall, see that you can write this information. Okay, so see that you have this down command and it will write this again. So as you go here in my airfoils, okay, see here that you will have CF and you will have that information, okay, for this specific angle of attack that we're installing. Okay, so I think at this point is all for this case. Okay, so in these first 3 videos we studied the most important things. Then the other videos are going to address a little bit now the other models that we have, menus or modules that we have here. So this one, complex mapping design, surface fit design. So this is for optimization. And this one, geometry design. Okay, how to modify the airfoil. Okay, so here, for instance, you want to change curvature, add flaps, slabs, stuff like that. You can do it. Okay, so it can be an airfoil generated using NACA, this function, or it can be an external airfoil. Okay, so you can control that with that. So this will be the subject of the next videos. Okay, thank you for your attention. See you next time. Bye.